Mrs. Brummel here. We're going to go through 1.5 today. So we're going to be investigating infinite limits and then limits at infinity as well. So we're going to use a table here to investigate this limit. So what happens as x approaches 0 for this function, 1 over x squared? So as I approach 0 from the left, okay, I'm becoming extremely large, right? 10 to the 6th, 10 to the 8th. So we can also say it as it becomes unbounded. As I approach it from the right, same thing is happening. Okay, another way to say this is we can say the limit as x approaches 0 of 1 over x squared, we can actually say that it equals infinity. Okay, this is proper notation. We actually can also say it does not exist. I personally like to do this more. It's a little bit more descriptive. So far, when we've done a lot of does not exist, it's been for like piecewise functions that don't meet. This actually lets me know, hey, my function's shooting off forever to infinity as I get close to x equals 0. So this is a little more informative, but either are acceptable on the AP exam. The first is just more descriptive about what's happening. Okay. Some things that are helpful to know. So this pattern, basically if I have 1 or a constant, it could be 2, 3, 4, 7, whatever, over x or over x to some power. If I'm approaching it from the right, so numbers that are greater than this value, it's going to be 1 divided by a very small positive number, okay? And what happens there when I do something close to 0 divided by, a constant divided by something close to 0, I get positive infinity. If I'm approaching 0 from the left, all that's going to change is my infinity will be negative, okay? So 1 divided by a very small negative value is going to approach negative infinity. Okay, so now we're going to investigate. Sorry, I have my Jersey Shore get up on, so ignore the Bengals. Okay, investigate the following limits. So as we approach 3 from the right for this function, okay, basically I still am going to use substitution, but I'm going to kind of think about this just more logically. Okay, so if I were to plug in 0, right, plug in 3, I would get division by 0. So I can't really evaluate this. This one also doesn't factor nicely, so we're just going to think about this logically. Okay, so if I were to substitute 3 into the numerator, okay, so 3 for x, I get 7, okay? So the numerator is going to approach 7. Numerator approaches 7. Okay? The denominator, okay, so if I'm coming in and I'm approaching 3 from the right, so there are going to be numbers just a little bit bigger than 3 as I approach from the right, I'm going to end up with a very small positive number. So denominator approaches 0, but we're going to say a very small positive number, okay? So when that happens, so we're saying we have a constant divided by a very small positive number, okay? That's exactly what we were saying up here. A constant divided by a very small positive value is going to go to infinity, okay? So we're going to say that approaches infinity. So this limit is equal to infinity, okay? All right. Now I have the limit as x approaches 1 from the left. Okay, so we have x squared, okay, over the natural log of x. Okay, so as I approach 1 from the left, so we have natural log of 1 is 0. So again, I get division by 0. So I want to think about approaching 1 from the left. So if we think about the natural log function, looks like this, where it crosses right at 1. So if I'm approaching 1 from the left, I'm going to be a negative value. So again, I have something very large, or when I plug in 1 here, so if I again think about the numerator, okay, if I were to plug in 1, the numerator approaches 1, right? 1 squared is 1. Okay, and the denominator approaches 0. okay? But again, it's going to be a very small negative value. So we're going to have a constant divided by a small negative value. That's the situation. So we're going to get negative infinity. Okay? All right. Next is a table. This is directly from your book, you guys. So it's just kind of reiterating when it's going to be negative versus positive. Okay? And that can kind of help you decide, is it going to be positive infinity or negative infinity? These are just kind of some generic statements to help you. That says when our limit of the denominator is 0, and we're approaching from the left versus approaching from the right. Actually, I think all these are left. Yep, approaching from the left. How does that affect our sign on infinity? Is it negative or positive? So those are kind of some generic statements to help you with that. What we're going to use limits for, especially in this next section, you guys, is for helping us determine vertical asymptotes. So we have a vertical asymptote at x equals c if the graph of the function f has any of these that are true. So if we find a limit as x approaches that value, goes to infinity or negative infinity, that is a vertical asymptote. So we are going to use limits to find the vertical asymptote for this function. So I have, okay, sorry, I'm making sure I'm doing that, yeah. Okay, so what I did on this one, you guys, just to kind of look at this a little more concrete, is looking at some values. So if I'm looking for the limit as x approaches 3, okay? So why did I pick 3? Well, 3 is what would make this denominator equal 0, right? So x equals 3 would make this function undefined, right? Is not, I would get division by 0. Division by 0. Okay, so those values are kind of what we want to look for. So I want to approach 3. So we're going to do the usual. We're going to pick some very close numbers to 3 that are less than 3, right? So we're approaching 3, and then we're approaching 3 from the right as well. So like 3.001, 3.01, 3.1. Okay, so if I were to plug these different values in for x into this function, here's what I get. So I got 290, 29,900, and then 2,999,000. Okay, on this right side, started at 310, then 30,100, then 3,001,000. Okay, so we can see these numbers are getting extremely large. So these ones are approaching positive infinity. So because we have the limit as x approaches 3 of x over x minus 3 squared, because we found that limit to be infinity, that means there's a vertical asymptote at x equals 3. Is a vertical asymptote. Okay, so limits equaling infinity or negative infinity indicate there's a vertical asymptote at that point. And again, we're kind of starting with things that make division by 0 happen. All right, we are going to look at this graph and table and investigate two one-sided limits. Okay, so they kind of did this in one row. So they did positive 100, they put that in for x, and it came out to positive 0.01. Then they put in positive 1,000, came out to 0.001, so on. Then when they did negative, it produced the negative value of that same thing. So as we look at x getting bigger, so another way to say this is x is approaching infinity. So the limit as x approaches infinity, and we're going to positive infinity, okay? I'm just looking at the positive one to start, okay? Of f of x, okay, equals, and actually I'm going to write the function, sorry. Our function's 1 over x, okay, equals 0, right? These are getting smaller and smaller and smaller. Now the limit as x went to negative infinity, so these negative numbers, negative 100, negative 1,000, negative 10,000 of 1 over x, also equals 0. Even though these numbers are negative, they're getting closer and closer to 0. which kind of makes sense, right? 1 divided by any large number, the bigger that number gets, the closer this fraction's getting to 0. So we're approaching 0, regardless of if it's positive infinity or negative infinity that we're approaching. Okay, also, we can see when I approach negative infinity, this actually indicates a horizontal asymptote. So at negative infinity, right, out here at negative infinity, x approaches negative infinity, right? My graph is getting closer and closer to 0. As x approaches positive infinity, going this way, right, my graph gets closer and closer to 0. So these indicate horizontal asymptotes. Okay, and we're going to actually talk about that a little bit more on the next page. These, you guys, are property. They're just saying that all those properties we've learned of limits also still apply even when we're approaching infinity or negative infinity. So these are also valid for x approaching negative infinity. They're just saying all the properties we were using before to algebraically manipulate limits still apply. Okay, these are ones that you guys want to kind of just know, I think, at this point. This is, and a lot of these, like I said, you can just think about them logically. Okay, so number 5, as x approaches infinity, this is the one we just talked about. So 1 over a very, very large number, that's just going to get closer and closer to 0 on both sides. Okay, now if I have a very large number divided by 2, so a very, very large number divided by 2 is going to be very close to that very large number. It's going to become unbounded. Okay, when I have a very large number divided by 2, but I'm approaching negative infinity, it's going to equal negative infinity. Okay, the square root, if I take the square root of anything and these numbers get bigger and bigger, my graph is still going up forever and ever. If you think about the square root graph, it looks like this. It's gradually going up forever and ever as I go to infinity on the right side. So this is infinity. Same with the natural log of x, right? As x approaches infinity, this graph also goes up forever. Gradual, but it does go to infinity. Okay, this also goes kind of with what we just did earlier. When I have a constant divided by x, this is going to go to 0. It also happens when I have something to a power. So even though it's to a power, if I put infinity here, numbers approaching infinity, 5 divided by a very large number is going to approach 0. Negative infinity, same thing. If these numbers get really, really big towards negative infinity, raise it to a power and multiply by 5, a constant divided by that is still going to approach 0. Constant divided by something very big is 0. Okay? Okay, last couple examples here, you guys. All right, so we are going to find these limits as x approaches infinity. So let's think about the ones we just did. 1 over x or 1 over x to a power, if x is approaching infinity, these are effectively 0. So this is going to turn to 2 plus 0 times 1/3 minus 0, right? This one and this one approach 0 as x approaches infinity. Okay, so we get 2 times 1/3, which equals 2/3. Okay, this one. Okay, what we want to look at is we actually want to look at the highest power of x. So I'm going to kind of show this to you longhand, and then kind of show you the shortcut that you can use as well. Okay, so basically I want to look at the highest power of x. So my highest power involved in this whole expression is x to the 3rd. We're going to divide every single thing by x to the 3rd. Now, why I can do that, why that's legal, is it's just like reducing fractions, right? When I reduce fractions, I can divide everything by 2, and it's still an equivalent fraction if I can divide by 2. We're going to divide everything by x to the 3rd to kind of reduce this fraction. So I'm going to keep my limit notation. Okay, so I've got 3x to the 3/2 divided by x to the 3rd plus 5x to the 1/2 divided by x to the 3rd divided by x to the 3rd over x to the 3rd minus x to the 2/3 over x to the 3rd. Okay, so remember when we divide powers, I can subtract the exponents. So this is going to turn into the limit as x approaches infinity this one's going to reduce to 3 over x to the 3/2 plus, subtract there, 5 over x to the 5/2. And we get 1, right? X to the third divided by x to the third is 1. 2/3 minus the third is going to be 1 over x to the 1/3. Oh, sorry, that's a minus 3. So 3/3 or 9/3. 2/3 minus 9/3 is 7/3. Okay, so to pick up here, you guys, we are kind of looking again for all these spots where I have a constant over x to a power. Remember, those are all 0. So this becomes 0. This becomes 0. We have 1, and then this becomes 0. So 0 divided by 1 is 0. So this limit, we'll put it up here, equals 0. Okay, so that is kind of long, dividing every single piece by the highest exponent. Basically, what you can always do is you can look at the highest exponent in the numerator and denominator. All of these, after I reduce, are always going to go to a bunch of zeros, but we need to check the highest versus the highest. So if I just look here, what's higher? If it's bigger on the bottom, essentially what's happening is I'm going to be able to reduce it to 1 over x to some power. And remember, if we're approaching infinity, this always will equal 0, okay? Okay, I'm actually going to skip down to 17 and come back, because 17 is another one just like that. So if I'm looking at this guy, I can kind of ignore the rest and just look at the highest powers. Now in this case, these powers are equal. So these ones, if I divided all of them by x squared, they'd just go to 0, okay? Just like we did kind of longhand in that previous one. But these ones, I'm going to end up with x squared divided by x squared, which is 1. So I'm really left with the 3 times the limit of x approaching infinity of x squared over x squared, because those other ones are going to 1, or going to 0, and that's just 1. So we end up with 3 times 1, which is 3. Okay, so the limit as x approaches infinity of this is 3. So we really just look at those leading, the highest power in the numerator, the highest power in the denominator, and compare. If they're the same, they reduce to 1, and then if there's a number there, we're going to multiply by 1. This one, we had a bigger power on the bottom, so the top's going to completely reduce down to possibly 0 or a constant, and the constant divided by a larger power when we approach infinity is going to be 0. Okay, this one, 18 as well, similar. So let's look at those leading coefficients. Okay, so I have leading powers, I should say. So highest power in the numerator, highest power in the denominator. Okay, so x squared over x to the third, right? That reduces to 1 over x. So again, really what I'm finding is that 4, I'm going to end up multiplying by it, but we have 4 times the limit as x approaches infinity of 1 over x. Well, we know that's 0, right? 4 times 0 is 0, okay? So that's kind of a shortcut to what I did longhand up here, is dividing every single thing by the highest power. We can just look at the leading powers, the highest one in the numerator versus the highest one in the denominator, and see what we get. Okay, last 2 examples. Thanks for hanging with me. Number 15. Okay, when we have a radical, okay, what I'm going to do is I'm also going to kind of reduce this one, okay? Actually, I'm going to rewrite this, you guys. So this, again, I'm kind of comparing the largest powers. This guy, right, this leading power right here, the square root of that is going to be 2x. So if I compare x to 2x, right, if we're just finding the limit of x approaching infinity there, remember all the constants are just going to end up going to 0, okay? Well, this, right, x divided by x is 1, so we're going to end up with 1/2. So again, we can look at those leading powers, the highest in the numerator versus the denominator, and we can just look at those to find our limit. Okay, last one, 16. Okay, this is going to involve a trig function, okay? So something to remember about sine and cosine. So sine lives between -1 and 1. So does cosine, right? And cosine is between -1 and 1. Okay, so that's good for us to remember. So as x approaches infinity, right, numbers on this interval, okay, they contribute very little, right? So these numbers are, I'm going to say range, right? Okay, so if I were to evaluate any sine function, this is going to be some number between -1 and 1. This is going to be some number between -1 and 1, okay? So 1 and -1 are going to contribute very little as we go to infinity, right? Just like this constant and this constant were irrelevant as we're going to infinity. They're so small. Same thing here. -1 and 1, any number between those, these are essentially irrelevant, okay? So they're going to contribute very little. And I'm going to even put 0 there, okay? They're going to go to 0 as I approach infinity. So basically, I again am kind of comparing those higher powers. I'm really just looking at this, the limit as x approaches infinity of x over x. Well, x over x is just 1, so that is going to be my limit. So just knowing that those live between -1 and 1, they're essentially constants in there, and so we're just dividing those leading powers again. Okay, thanks for hanging with me, you guys. That's all for 1.